So today I will talk about our work on verifying symbolic computation in the HolPy theorem prover. So I'm from the Institute of Software of Chinese Academy of Sciences. So the outline of the talk is as follows. So first, I would like to talk about a very large-scale project that I've been working on, which is the HolPy interactive theorem prover. Just to give an brief introduction to this project. And then I will talk more specifically about verification of definite integrals in HolPy. And then I will continue with describing some of the recent extensions, most of which have been completed in just last 2 months to the verification of definite integrals tool we have here. And finally, I will discuss, end with the discussion and some suggestions for future work. Okay, so all these projects have been done with collaborators and other students in various institutions in China, as listed here. And throughout this talk, I will try to give some demo of our tool live. So I hope this goes well. It will be fun, and it will be also fun if there are some problems to see. Yeah. So first, so let me start with giving an introduction to HolPy. So this is an interactive theorem prover whose development started in about 2018. It is implemented in Python and with the user interface part implemented in JavaScript. So HolPy is the underlying logic is higher order logic. So this is very similar to other tools like Isabelle HolLight, and so on. So the main point of this project is not to explore a different foundation, but rather in the last 2 points listed here, which is, first of all, we build a Python API for writing proof automation, so people can write new proof automation to extend the tool by writing code in Python. And finally, we also would like to try out the different designs of user interfaces within HolPy. And notice the plural here. So one of the ideas is that perhaps we should have several different user interfaces for different purposes for interactive theorem proving. So speaking of user interfaces, currently the user interface in HolPy for general purpose theorem proving. So in basically matching what Isabelle or Koch or Lin can do is looks like this. But I would not have time to talk about it extensively here. So maybe this is a topic for another time. The other point that I do want to take some time to mention is that the Python API for writing proof automation. So the point is that the user can extend the tool with the new proof automation by writing Python code, but we still try to follow this something called LCF architecture for designing interactive theorem provers. So the correctness of the tool does not depend on the proof automation code that the user wrote. It is still guaranteed by checking the proof terms either internally or by third-party tools. And so the Python API consists of, so the way people can extend proof automation is by defining new Python classes for conversions, macros, tactics, and so on. So if you are familiar with how to write new proof automation in Isabelle, for example, these terms would be, well, except for macros, the other terms would be quite familiar to you. And because Python is sort of, I think it's mainly still an imperative language, but we support multiple styles of constructing proofs. So whether it's a top-down or bottom-up or a functional or imperative way of writing code. And this shows a brief example of what it looks like to write proof automation using this Python API. So the example shown here is implementing a conversion. So this is a procedure for rewriting terms. And here the purpose of the rewriting is to normalize an expression that consists of additions. So building on this, we could eventually implement something that proof automation that rewrites an expression to normalize it with respect to associativity, commutativity, and the distributivity of addition and multiplication. And this is actually one reason I mentioned here is that this is actually well figured in the proof reconstruction process that I will mention later. Okay, so this I think is a very brief introduction to the features available in the HolPy project. And now, okay, so I guess this is showing that the various minor points in this code, including that we can do various case analysis on these terms and apply existing theorem and apply existing conversions in the code, just in a way that is very similar, I hope, to implementing proof automation in Isabelle or in Lean. Okay, so now I will move to the main part of the talk, which is describing this tool that we built for verification of definite integrals. So the motivation of this project is that we want to explore design of user interfaces and automation in the verification of symbolic computation. And symbolic computation compared to, say, the full mathematical language, it can be seen as a relatively limited language. Nevertheless, this limited language can still have a very wide application area, whether in verifying parts of mathematical proofs or verifying calculations in science and engineering. And so our goal is to be able to let users to perform computations step by step in a familiar setting like computer algebra systems, but with the results that are potentially checkable by conversion to lower level logical systems. So I think it's the point is that it's a mix of the experience should be a mix between using computer algebra systems and between interactive theorem provers. And the potential application that we are thinking of can include things like verifying computations in engineering. So for example, we may be interested in the design of feedback control systems. And in textbooks for feedback control systems like this, we would frequently see computations like this, and we may want to be able to verify all these calculations are correct. And of course, we may one application because it's for integrals, we would also like to verify, for example, formulas in this table of integrals, series and products, and featuring formulas like this. And as you can see, the formulas can still have some more complicated structures. For example, for many of these identities, this evaluation of the integral, they can evaluate to different forms depending on different conditions on the parameters. So we would like our tool to be able to describe all these features. Okay, so the basic idea of our tool is in a way is still very similar to how an interactive theorem prover would work. So the process of doing this symbolic computation is through an interaction between the human user and the computer. What the user does is they would specify the steps of computation as well as the parameters, possible parameters the steps would require, and the computer could suggest choices at any stage of the computation and apply the choices or the steps that the user made, and also display the results to the user. So this is this mutual interaction process that is also very similar to interactive theorem proving. And let me give a more specific example. So for example, one of the very popular steps in doing integral is integration by parts. So for example, in computing this integral, after 2 steps, we would end up here, and we would wish to again apply integration by parts to this expression. And the way it works in our tool is that at this stage, the user would select integration by parts from the menu, and then the tool would give this dialog that queries for the parameters that are required. In this case, the expressions u and v, such that u times dv is the integrand. So the user can enter the expressions in the dialog here, and the tool very helpfully shows the LaTeX form of the expressions. And all this will be shown in the demo later. And this is another example that shows a more complex interaction process. So in this case, we wish to apply a trigonometric identity to rewrite the term. So for example, the calculation has already proceeded by 4 steps. And here we wish to apply a trigonometric identity to rewrite the cosine square in the numerator. So the user selects apply identity, and then in this text form here, selects the separate expression that the user wish to rewrite. And then on seeing that, the computer can display a list of choices depending on the identities that they know. Okay, so of course, currently the user interface works like this. We can certainly imagine that if our technology improves, so perhaps the user can directly select on the LaTeX form of the expression. So I think that is just a matter of designing the figuring out how to extend the LaTeX display package to allow the user to select expressions. So right now we don't know how to do that, so we just allow the user to select text here, which I think is still sufficiently convenient for our purpose now. Okay, and so that is what we have described so far is the part that the user sees, and in the background we also have mechanisms for making sure, try to make sure that the computation that the user did is correct. So first of all, of course, whenever the user applies some step, we do some checks that the step that the user enters is correct, and also, of course, we compute the result of the computation. But if we wish to if we wish to prove that this computation is correct in the sense of in the standard of interactive theorem proving, then what is necessary is to reconstruct the proof from the sequence of computation steps. So if you are familiar from the interactive theorem proving community, this should be quite familiar to you. So from the sequence of computation steps, what we need to do is to automatically reconstruct proofs in a higher order logic or in some other logical foundation. And this is possible because in the from the tool, we can obtain all the necessary information of this sequence of from this sequence of computation steps. So given a computation, if the main tasks that we still need to do in order to reconstruct proofs include the following. For example, proofs for simplifying or rewriting of expressions, including the normalization of arithmetic expressions that we mentioned before. Proof for inequality checking, and also checking various side conditions. So applying the theorems of integration and also checking various side conditions, such as continuity, integrability of the functions. So all this we have been partially completed. So we do have proof of concept implementation using Python, using the API for writing proof automation that I mentioned before. And it is able to reconstruct the proofs in many of the simple cases. And all this proof reconstruction relies on a mathematical library consists of theorems in analysis. And this part is still a reconstruction, but we can imagine that this is something that is very standard and has been repeatedly done in Isabelle, Koch, or Lin, and other theorem provers. So in summary, the overall architecture of our tool can be seen in this like this. So it is a layered architecture where the central part is this language of computation steps. So we define a custom language for our tool for mathematical expressions and the rules of computing integrals. Above this level, we have the user interface where the user can perform computation by choosing action from a menu, which would form the sequence of computation steps. Below this level, from the sequence of computation steps, we have automatic procedures for constructing proofs that are written in Python, and this would yield a proof in higher order logic, and this proof would depend on an analysis library, which consists of theorems in mathematical analysis. And as I said before, the completion of this library is still work in process. Okay, so I think that gives a brief introduction of our tool on slides. So next, we can try to proceed to the demo part of the talk. The first example that I wish to give is perhaps this is a very popular kind of problem that we can use to trick undergraduate students in a calculus class. So this is a computation of the integral square root of 1 plus cosine of 2x. And through these seemingly innocent steps, we get an answer of 0. And of course, the answer here is not 0 because we are integrating from 0 to pi, and the integrand is clearly positive in the entire region. Okay, so I hope I wouldn't try to test everyone here because everyone here are many of professional mathematicians. I believe that many have certainly seen what is wrong here. The mistake that we made is that we simplified the square root of cosine of x directly to cosine x, but this is possible only if we know that the cosine of x is positive, is not negative. But this is not true in the entire region of integration. So the correct computation would work something like this. The main the main point is that after the simplification, we need to split the integral like this, and finally be able to complete the computation. Okay, so now let's see how we can do this integral in our tool. Okay, so this is the user interface here, and we just go to the integral that we want to do. And this is already done, so I just clear the calculation here. And so starting from this expression, the first step that we need to do is to use a trigonometric identity. So I click on this menu and apply some identity and select the cosine of 2x here. And now the user interface gave us two choices. And the first one is what we want. So we click here. And now we do a simplification. And notice here that the tool correctly notices that we cannot simplify away the absolute value sign here. If we try simplify again, nothing happens, showing that this cannot be cleared away immediately. And so what we need to do is to apply another rule for integration, which is splitting the integral into two parts, splitting the region on this point pi over 2. Okay, once we have done that, and again, if we simplify, we can clear away the absolute value sign with the minus sign in the second term. And now we can apply identity for definite integrals and simplify again to obtain our final answer. Okay, so I think the first example we wish to demonstrate here is mainly to demonstrate that the whole computation can be completed just by clicking on the menu and selecting the choices that the computer gave, which is very, in this case, very convenient for the user.
was one,
Okay.
yes.
Yes.
There was one
question.
There was one human step that you used where you had to choose pi over 2 as the step.
Yes. Yes.
So is there any way to automate those choices of
Yes. Okay. Yeah. Thank you for the question. Yeah, certainly. In this particular case, we can try to automatically detect the splitting point here, because we would notice that the sign of this cosine of x changes sign at the pi over 2. And actually, in the previous version, we actually do have this automation here. But you can also imagine there are cases where the automation may not be able to figure out the right splitting point that is desired. So in this case, the human still needs to provide the splitting points. So certainly we can add all kinds of automation further into this tool to reduce the number of steps that the user have to take. But I believe that there are in the end there are still some other steps that we still need human intervention. Okay. Okay, so the second example, I think, is an illustration of the advantages that is provided if we have interaction instead of trying to only have full automation, like a computer algebra system such as Mathematica. So this integral here appeared on the competition called MIT Integration B, I believe in the year 2019. So this is an evaluation of a definite integral, and the problem itself is not actually complicated if you notice the main trick, which is to apply the sum to product identity to both the numerator and the denominator, and then the cosine of x over 2 cancels, and we can do the standard substitution to get the final answer. So I think so if you try this on at least the online version of Mathematica, the Wolfram Alpha, it is unable to produce the closed form answer. So I believe the reason is that the Mathematica would try to apply some very complicated automatic algorithms, which would take a very long time, rather than noticing the trick that is available here. And we can see how we can do this integral very quickly on this user interface. So we just go to this problem set and click the computation. So again, the first step is we try to rewrite using this identity here. And again, the user interface is able to give the suggestion of using the sum to product identity. And we perform the rewriting again, this time on the denominator. I chose the wrong one. Okay, and now we just simplify, and it notices that cosine of x over 2 can be cancelled, and we do a substitution, substituting u for a cosine of 39 over 2 times x. And the final step is to apply the definite integral and simplify to give the final answer. Okay. Okay, so this gives an overview of the tool for computing definite integrals that we have actually already finished in 2021, so about 1.5 years ago. And so as we have seen that what this tool allows us to compute individual integrals in a user interface that is something like a computer algebra system, but also it allows user to perform the computation step by step. Now, the above work is still limited in the following ways, especially compared to a full interactive theorem prover. And so the first issue is with the extensibility. So all the variable functions and identities in the tool that are given here are hard-coded in the Python code rather than allowing the users to extend with new functions and identities. The calculations are also independent from each other, so there's no use of results. So for example, if we show an integral in a previous problem, so we are unable to reuse the result in a problem that in a subsequent problem. And also, of course, the range of multiplication is limited because we can handle definite integrals on finite intervals only. Okay, so in order to address these limitations, we have extended these tools in many ways in the past half year, and in particular in the last 2 months. And the first major set of extensions we made is to introduce a system for managing definitions, identities, and proofs. So for example, now in the new tool, we can define new functions and state identities about these functions. We can manage conditions of identities, which is a very important part once we get to more non-trivial functions, many of which are, and more non-trivial functions identities, many of which are only valid for certain ranges of the parameters. And we also notice that there are many problems in symbolic computation that nevertheless involves induction. So for example, there are identities that has an integer parameter n, and the way to show this identity is by induction on n. And so we have added support to all these functionalities. And what is interesting is that in the process of adding them, we are making our tool to become more and more like a regular interactive theorem proving systems. So I guess the one lesson that we learn here is that I think there is a core subset of functionalities that interactive theorem proving system must have in order to have to meet basic standards of extensibility and reusability. And in particular, this includes allowing the user to define new functions, managing conditions, and so on. And another set of extensions that we have added is extending our range of application from definite integrals to improper integrals and limits and indefinite integrals. And we also have some basic support for infinite series, including including Taylor expansions and the evaluation of infinite series. And also we added various other tricks, added other steps that allows us to perform some of the more tricky definite integrals. So for example, swapping integration and differentiation, and swapping integrals and sums. And so currently we have 27 rules to choose from the menu. And so as we can see that even with the expansion of the functionality that we have here, we still try to keep the number of rules that we have relatively small so that it is manageable for the user. And one of the main motivations in this part of our work is to try to formalize the various examples from this very nice book called Inside Interesting Integrals. And what this book does is that it describes the computations for various tricks. It describes various tricks for computing definite integrals, and it includes very concrete computation steps for these integrals. And we have performed over 50 integrals from this book, covering topics like standard ones like partial fraction decomposition, as well as more advanced techniques such as differentiating under the integral sign or using the power series in integration. And we have also gone to deriving some standard properties of special functions, such as the gamma and beta function. So one current important limitation is that we so far does not handle complex numbers and contour integrals. So this is certainly one of the major things that we would like to add in the future. Okay, so now we go to some examples from more advanced examples from the Inside Interesting Integrals book. So this example is a very standard application of power series to evaluate an integral. So to evaluate this definite integral, which could not be done in closed form without using some very advanced special functions. We first expanded the Taylor series for the log function, and then after some simplification, we exchange the integration and the sum, perform the integration within the sum, and then we notice that this is an infinite series that is alternating sum of square, which can be evaluated directly to be pi over square over 12. Okay, and now we see, let's see how this can be done in our tool. Okay, so first of all, let's see some other parts of our tool, which is that, so we can see that our user interface, we have several different what we call books, or we can, it's sort of like series or collection of theories in interactive theorem provers. In particular, we have a base theory here that contains some of the standard identities that we assume as axioms, and all this will be can potentially be used when we choose things like indefinite or definite integral identity or evaluation of series in the future computations. So in particular, we see that we have various, let's see where it is. Here it is. So we have the series expansion for the log function here, and also some evaluation of series like here that can be used later on. And now if we go to the problem that we have here, and this problem, and we clear the computation. And so the first step, if we remember from the slides, is to, okay, first of all, the first step is to specify that we wish to do this equality, derive this equality by computation, by computation on the left and the right hand sides. And then on the left hand side, the first step is to use the Taylor expansion for the log function. So we do the series expansion, and we select that we wish to expand the log function. The index variable is fine, and this allows us to expand it like this. And then we do some rewriting here to move this 1 over x inside the sum. Okay, so this is somewhat a manual step that the user have to do, and that perhaps we could eliminate by improving our automation in the future. So after doing this rewriting, we can now exchange the integration and the sum sign, exchange sum and integral, and perform another simplification. And now we notice that the integral is something that becomes something that the system is able to do. And so we apply definite integral identity and simplify again. And finally, we obtain a series that we see that is already included in previous theory. So we can just directly use series evaluation, and it is able to find the series evaluation that is available and give us the final answer.
I have a question. So
yeah.
Does this tool, is it able to convert these steps into formally verified truths? Because the The interchange of the integral and sum is not trivial here.
Yeah, that's very good question. Yeah. So certainly this part is we haven't implemented yet. So before we have implemented conversion for other steps like simplification or applying substitutions, but this step we haven't done the conversion, and this is something that we do plan to do in the future. So I believe what we need to do here is that we need to describe precisely what the set condition for this change here for this change is. I believe there is some convergence conditions, and then perhaps we need to incorporate some automatic ways to derive convergence conditions. And so certainly that are other things that we need to do in order to produce the formal proof from this. Yeah, so certainly you are correct that we haven't been able, this part is not done yet. Mm-hmm. Okay. And in our next example, we wish to show a different kind of example where the calculation isn't just a single calculation, but consists of several steps. And in a mathematical text, we would have some other descriptions about what we do in each step. So for example, the goal here is to evaluate the following integral. And the method here is this trick of differentiating under the integral sign. So we're differentiating both parts, and then we move the derivative inside again as the same thing as in the previous question. Here, there are some set conditions that need to be checked for this exchange to be valid, and currently our tool does not support checking these conditions. So this is also something to be added in the future. And after this exchange, we can simplify and evaluate this integral. And then, because we know what the derivative of I is, we can integrate both sides to get that the IA should be equal to the integral of 1 over a plus 1 plus this constant. So it's log of a plus 1 plus a constant. And then the trick is that we evaluate this equation on a particular value of a, which is a equals 0, to obtain that the constant must equal to c. And this gave us the final answer, which is that I of a equals log of a plus 1. Okay, so this is a standard trick if you have seen it before, but we can imagine that again, this would be a very long process to formalize if we are just working with a standard interactive theorem prover. And now we can see how this can be done in our user interface. I believe this is here. Okay, so again, the calculations are done before, so let me just clear all the steps. So first thing we notice that is that because the computation is not done in a single series of computation steps, but through various steps that are linked together by some mathematical reasoning. So we also see here that we divided the computation here into several steps. The first step is to, after this definition, the first step is to evaluate the derivative of I. And here, this is a standard computation. And so I just go through this quickly. So we expand the definition here and simplify, which automatically moves the derivative inside the integral and evaluate the derivative. And now we can evaluate the definite integral and simplify. Okay, so this is a pretty standard step. The next step is the main trick of this computation, which is we need to integrate the previous equation on both sides. And so what we do what we can do here is to prove by rewrite goal starting from the previous lemma. And then we integrate both sides and perform an indefinite integral identity, okay, to obtain the final answer. actually not the final answer because we need to simplify away the absolute value sign here, which we can do because we have the condition a greater than equal to 0 in this goal. And so the system is able to notice that and simplify away the absolute value sign. Okay, the next step is to substitute a for substitute 0 for a in this equation to figure out c equals 0. So we start another computation and do another proof by rewrite goal starting from here. And then we do a variable substitution for a goes to 0. And we also need to expand the definition of I here. And now this allows us to do the simplification. And finally, this is something that can be improved. We need to move the c to the left side of the equation. And we can do this by another step like this. Okay, and finally, we can just use the previous results to obtain our final answer. So this is wrong. We need to use this lemma here to use this lemma first. So we select the expression and select the third lemma here, which applies the lemma, and then we rewrite c to 0 by applying lemma again. And finally simplify. Okay. Okay, so this is showing the important part in this computation. So what we have done is exchanging the derivative and integral, and in this evaluation of indefinite integrals, we end up with this plus c here, and this is actually important because in some other computations, this value of c may be some other value, and we need to figure it out, and so we need to solve for the value of c in the as a part of this computation. So again, to address the question that is similar to before, there is the issue of how do we generate a formal proof from this process. And certainly one issue that should be addressed is what is the meaning of this plus c here in solving this indefinite integral, and what is the formal meaning of this solving for the value of c here. So what we are trying to do in our tool here is that first we try to first implement our tool in such a way to make the user interaction process similar to what regular mathematician would do. And then after that, we could try to make this process, try to understand this computation steps in a formal way and try to convert this in a formal proof. So certainly, again, this is something that we would try to do in the future. Okay, so now the last example that wish to show is reasoning about the gamma function. And this is an example where we define the gamma function and then we obtain some identity of this function by induction. And finally, as an application, we can evaluate this tricky definite integral in terms of the evaluation of the gamma function. Okay, so now I see that I'm sort of running out of time here. So I would show only the, let's see, maybe the induction step and omit the other steps. Okay, so I'll just go over the other parts. So for example, in showing this standard identity, we would do this integration by parts on this improper integral, and then this would give us this identity. And then in showing this final calculation here, we would do this substitution and rewriting this formula to this formula from here, which allow us to apply this identity to get the gamma of 4 over 3. Okay, and for showing this identity here, which I should add is only showing this quantity only for the for natural numbers greater than or equal to 1, we could apply the proof by induction. And the system allows us to specify the induction variable and starting from 1. And then for the base case here, we would expand the definition. And well, this is relatively standard. And finally simplify. And then for the induction case, we would, I believe, first apply this lemma here that we have just shown, and then simplify. And now we use the induction hypothesis, which is one of the steps that we can choose from the menu. And finally, we apply identity for the factorial. So again, using the same menu item. So apply identity. And again, the system suggests us that this can be rewritten to n factorial. Okay. Okay, so this finishes all the demos thankfully without problems. And okay, so now let me give a brief summary of this talk. So what I've presented here is sort of an interactive theorem prover in quotation marks designed specifically for symbolic computation. And the main goal that we would like to achieve in our tool is to have a user interface that displays formulas in LaTeX form and have task-like automation that would help users with the simple tasks in the process of symbolic computation. And eventually, we would hopefully try to generate higher order logic proofs that can be checked independently. And as I said before, this is currently implemented only for the simple cases, only for the simple steps of computation. And I think a very nice thing about this design is that what we wish to achieve is to divide the task of producing formal proofs for symbolic computation into several different parts. Each of which can be done by users or developers with different kind of expertise. So the whole process of computing integral is from the user interface. The user would specify the steps to perform, and then this would yield a sequence of computations in terms of this intermediate language. And then from this intermediate language, we use proof automation to convert this to a high order logic proof. And finally, this high order logic proof relies on mathematical theorems that are proved using interactive theorem proving. And in a comparison with the regular computer algebra systems, in our system, we permit more manual control of the computation. So we have less automation, but by taking advantage of the human expertise, we could potentially perform even more complicated or longer computations than can be done in regular computer algebra systems. And actually, I think this interaction between computer algebra systems, or maybe like a similarity between computer algebra systems and our tool here, in the sense that many components of computer algebra systems, such as simplification, pattern matching, taking conditions, taking limits, and so on, must be needed here. And currently, we use simple implementations of these procedures. So certainly, if we incorporate this functionality, the full versions of this functionality from computer algebra systems, this would potentially significantly improve the level of automation in our tool. And of course, if we want to generate proofs from these procedures, it is important to have proof generating versions of these procedures available. And finally, I would like to discuss some potential future work. So I think one immediate extension that we would like to do in the future is to extend the tool to handle other kinds of computation, such as linear algebra or complex analysis or probability. with application to symbolic computation in mathematical proofs, in engineering, or even in machine learning algorithms. And this other potential interesting application is a potential application in education, which we can certainly discuss further. And I think the main point is that we can try to build tools that are immediately useful without achieving full rigor right away in the sense of interactive theorem provers. And of course, in order to actually achieve full rigor, we need, first of all, proof reconstruction for all the procedures for class procedures that I mentioned before, and also a library of mathematical theorems covering the foundational rules. And certainly, I recognize that this is a very large-scale engineering that need to be done to complete this. And another interesting thing that we can explore is that perhaps we can integrate this kind of functionality within an interactive theorem prover. So, for example, when proving theorems in an interactive theorem prover, we can switch between the general purpose mode that is kind of standard that we have now, and the symbolic computation mode, where we begin to display equations in LaTeX and allow user to perform steps like I've shown before. Okay, so certainly all of this would require a lot of work to complete. So finally, I would like to say that all our tool is available open source, both on GitHub and on Git, and we welcome contributions from others in order to improve our tool in the future. Okay, so thank you. So this is all my talk, and thank you.